Hello, good morning. I see a green bar, which means I believe you can hear me now. Welcome to another episode of Coding Rainbow. This is episode number, I have no idea, but I'm numbering the episodes now, and next time I do a live Coding Rainbow, I'll look at the number beforehand so I can say what number it is. But it is Tuesday, June 21st, on a very hot day in New York City. It's the morning time for me. It is possibly the afternoon or the evening time, or you might be at some point in the future where the times of the day don't matter anymore. I'm watching this as an archive. It's very hot. I have a cold. I don't know how today is going to go, but I do have a list of things I would like to cover and discuss. But before I get to that stuff, let me just do some quick business. Number one is if you are watching this as an archive, you can check the time code, the description of this video, which will have time codes, so you can click around and find the important pieces of it. Also now that I've said that, I want to check the chat here and see if in the chat, please tell me, can you hear me? And also I want to do a sound check, even though actually I'm not sure if I'm going to do any sound programming examples today, but how's the balance? Welcome to
Coding Rainbow.
Coding Rainbow.
with me.
The
Schiffman.
Ella.
How's the balance of the volume of the music, the volume of me? It's so much louder today on my computer. It's interesting. The other day I could barely hear the sound out of my computer, but it was too loud here. I don't know what's going on. Okay. Okay. All right, everybody settle down. Be nice to each other in the chat, please. I don't want to have to start banning people. Okay, so here we are today. Make what more loud? Okay. So I have a few things on my mind today. If this is new for you, if you haven't been here before, this is a YouTube live stream where my name is Dan. I make programming examples about a variety of different topics in the kind of creative coding space. And so I have a few things on my mind that I would like to look at today. And let's talk about what some of those things are. All right, first I'm going to check here. I'm just going to check and make sure everything is looking okay. I see that I'm streaming here, and I'm just always checking Twitch. I think I got to stop streaming to Twitch. Nobody's there. Sound levels are good. I see the chat going. Okay, so I think what I'm going to start with today, which actually I'm going to check. I posted a Twitter poll very briefly, and I'm going to check that. Actually, we can just look at it together. Let's look at it together. I have a separate computer here. I have my private computer here for things I don't want you to see. But this I feel perfectly happy to look at with you guys. Okay, so I'm going to go to twitter.com/Schiffman. And I'm going to look here. And so look at this. So these are some topics that I'm thinking about today, and it looks like you can get your votes in now, 27 votes. It looks like people are certainly very interested in the Perlin Noise fields. Now, I'd like to do a little quick anecdotal poll with the chat, and sort of get a sense. Like one thing I've been thinking about is just kind of I have a Perlin Noise terrain generator example. Let's take a look at that very briefly. So something I did. Let me open up here, terrain generator. So this is something that I did as a video tutorial probably a few weeks back, which uses Perlin Noise to generate this kind of continuous terrain and have this appearance of you flying over the terrain. But I kind of jumped right into what's required for this is two-dimensional Perlin Noise. And the Perlin Noise flow field example that I would like to do today, if I can pull that up. I believe I already have it open somewhere here. Here is a version of that example, which is kind of generating this kind of hair-like pattern in a processing window. This also requires two-dimensional Perlin Noise and is built off top of an example that I have, which I'm going to open up. Which is part of the Nature of Code book under Chapter 6 Agents, Flow Field. So I'm going to open, it's built on top of this particular example, which is showing you a lot of triangles kind of swimming around a space, a Perlin noise field. Okay, so this is kind of the topic. I've done other videos related to this topic, but I was thinking that maybe, and I want to hear from you in the chat, it does look a lot like hair, says Mytilene Video. What I'm thinking about is actually taking today, which is about 11:20 a.m., and I have at least an hour and a half here, to actually start from the beginning and do maybe a sequence of videos where I look at just what is the Perlin noise algorithm itself, how is it calculated, how does it work in processing and P5JS, and then what does it mean then to have Perlin noise in 2 dimensions or 3 dimensions, and then actually build this flow field example and then make the hair-like thing from that. So I was thinking about doing that today, and I don't know, I guess I'm curious to hear from those of you who happen to be here live. There's 49 of you. If that might be of use to kind of start a bit from the beginning. So I'm gonna answer some questions in the chat while you guys are thinking about that. So Ruby in the chat asks, is this a newer version of Nature of Code? I saw you are working on a P3 version. Okay. So let me take a moment to introduce myself a bit and give some background on some of these things for those of you who know. So first of all, what I'm talking about doing in terms of Perlin noise relates very much so to a book that I published a few years ago called The Nature of Code. This book is entirely available for free online. You can just take these sliders and slide them down to 0% and download a PDF. You can, without even bothering with that, you can go to Read Now, and you can see the chapter that I'm referencing here is this chapter on autonomous agents. And I believe somewhere in here, if I scroll down, there's a bit of an explanation about 2D Perlin noise, and at some point I even want to see, come on, load. This should load as an interactive example, but it's having, as I heard the other day, demo-itis, which means when I'm trying to get it to run, it's not running. So anyway, so this is something that's available for you. I encourage you to look at. Why was I mentioning this? So the question. Okay. Oh, there's a lot of questions going on. I got to keep a mental list of these questions. Both XP, I see your question. Okay, so there was a question about whether I'm working on a new version of this book, and in fact I am. Mostly there's just a lot of corrections and mistakes that were in the first edition that I'm fixing up and cleaning up the design and doing some things like that. And then I'm also going to make a version of this. This book is written with all of the concepts apply across many programming languages, and they're really at a core it's a book about algorithms and ideas. But the code for this particular book is all processing Java based. So I am currently working on a JavaScript version of this book, which I hope to have out by the end of the summer. Some people have asked if they can help with that. And so what I might take some time, I don't want to do this now because I'll get totally distracted, but if you're still here in about an hour or so and I'm kind of wrapping up, I might show you a bit about where all the GitHub files for the book are, this thing called Magic Book that I'm using to build the book, if people want to kind of contribute with pull requests and that type of thing. Okay. Triple X Gaming, I see you're asking a question over and over again in the chat. If you could do me a favor, and if you want to just drop me an email, I can try to, or post this question to the forum.processing.org and email me a link to your forum post. I'm sure I can help you with what it is you're asking about in terms of Java. Okay, so okay, so I've already taught the flow field. There's a Hebrew name that my Hebrew lessons from my bar mitzvah many years ago are not good enough for me to pronounce it. When did I already teach the flow field? I mean, I did it in the Cadenze course, and I've done it in an old Nature of Code video. But I do want to do it again, I think, with some new stuff. Okay, both XP had asked, there's so many questions today. Both XP had asked about shader learning, and the site that I mentioned is called The Book of Shaders. So I'm going to just Google that. Oops, no, and it's bookofshaders.com. Oh, this is the editor. Look at this. Wow, very nice. So this is what you should look for if you're interested. This was a resource I mentioned about learning the basics of shaders. I saw recently a demo by Matthew Caney, who is developing a shader framework for P5JS. And as soon as that gets further along, and as soon as I finish reading the book of shaders, I plan to do some tutorials about shaders in P5JS. Okay. Okay, so here we go. So what I would like to do, I know that I've done the Perlin Noise stuff before. The reason why I'm doing it again is twofold. One, let's look at Perlin Noise Shiftman YouTube. So there is this particular tutorial, which I'm going to somewhat do again. The difference here is this was made, even though it says 2015, this was actually probably recorded several years ago, and my video recording technology was not as good then. So I think it's kind of worth an updated version. It's also using processing Java, and I could do it in JavaScript, which I think might be nice to have that as well. The other thing that I did do is record a set of tutorials on Perlin Noise with Cadenza, but that's part of a separate company that owns those videos and owns that course. So I'd like to have that also as part of my YouTube channel. Okay. Okay, thank you. Oliver is chat admin now, and thank you for managing some of the craziness that's going on in the chat. Okay. Okay, so let's go here and let's get started. Let's all take a moment to meditate or perhaps dance to relax. Okay. Caney is spelled K-A-N-E-Y, I believe. Okay, whoops, I'm on the wrong computer. Sorry, everybody. Sorry, everybody. I'm trying to look at the chat. I probably shouldn't look at the chat so much. I'm using a MacBook Pro, I think it was asked. Okay, let's see. So I'm going to close this, close this, close this, close this. Close this. Nope. Okay, I'm going to minimize this. I'm playing some music while I'm getting set up here. I'm looking for, yes, here we go. Empty example. Okay, so it was asked in the chat, what language is your main programming language? I would say the one that I learned the most on and started with, it was Java, and processing, which I probably used the most in my life. This icon over here is built on top of Java and is the Java programming language. The thing that I might be using more of now these days is JavaScript, in particular the P5JS framework. And so those are the two things that I'm focusing on in this video tutorial series. However, this fall, I do plan on doing some, maybe I can show a little bit of this today. I've been working with Computer Craft in Minecraft, which is actually using the Lua programming language. And people have requested some C++ tutorials. I might consider that someday. And I will be doing in the fall more with Node.js, which is also JavaScript. Okay, here we go. So let me see here. Let me open this up in Atom. I'm using the Atom editor. I was going to do a CodePen tutorial. Hold on. Let me open up Atom. And I'm going to open this one up. Where's Atom? Somebody show it to me. Here it is. Okay, I'm a little lower energy today. The dancing is a little bit pathetic. Can you hear me sniffling? I don't know where I got this cold from. It could be allergies, I'm not sure. Okay, so let me see here. Now I want to make sure, I'm going to run a little local server. And I'm going to open up my web browser here. Where's the web browser? This is my sound effects panel. This is my web browser, window, localhost. And where am I? Perlin Noise 1. Okay. Let's see how that poll is doing. Okay, now let me just make sure this is really working. There we go. Okay. Oops. I got the console and I got the browser going, and I think we are just about ready. Let me see here. There's my code window. There's my browser window. I don't like having this extra style thing. I like having the DOM libraries and the sound library just in case. Whoops. What did I do? What have I done? Okay, there we go. Ooh. What is going on here? I'm not going to worry about it. Okay. Hello, everyone. I'm back. Yeah. Yeah, I don't know why I use background 51. Dragon Hunt 3 asks, what is Perlin Noise? Thank you for asking that question. You have just indicated to me that it is worth taking today. Today is the day about Perlin Noise. So first I want to show you something. I feel like there was, I'm going to Google Hugo Elias Perlin Noise. This is a, ooh, no, don't be gone. This was the page, maybe it's here. It's gone. This is a nice page. But this was this page right here. Can anybody Google Hugo Elias Perlin Noise and see if you can get to this page. It's so sad it's not there anymore. This is the page that I always refer to because I don't know, this is old. This web page has been around for over 10 years. And every time I want to look at how the Perlin Noise algorithm works, I always go there to give myself a little refresher. It's like a one-pager, and it's really nice. Wayback Machine, good idea. I don't want to get too distracted with this, but I will look for it. Let's see if I can find it. All right, somebody find it and tweet me the link or something if you can find it. But okay, so I'm going to talk about what Perlin Noise is. I can do it without that page. I will need a whiteboard. And I'm over here. And okay, so Buddha, yes, the Buddha brought has been requested a lot, and I would like to try to do that. Use the cache. Oh. Try that. No, usually there's a cat. I don't see where that is. Usually it shows me the cache. Okay, I'm not going to worry about it. Okay. Whoops, I can't see things. I have a cold, yes. Thank you, everybody. Oh, I'm on the wrong screen. Here I am. Okay. I have some lights that are not on, also to make things a little bit brighter in here. I don't know if these are helping. Okay. And I'm going to open up. Sorry. Okay, so you haven't, Muhammad asked, what did I miss? Unfortunately, you didn't miss anything. I am wearing pants. They are shorts. I have rainbow socks, by the way, but I'm not wearing them today. My daughter bought those for me. She didn't buy them because she was only 4, but I mean, whatever. She picked them out. Okay, the point is, I have rainbow socks. Welcome. So I'm going to get started now. I'm going to cycle the cameras. And so what I'm going to do is a multi-part series, a multi-part video to look at eventually how to do a Perlin Noise field. And this is, a kind of classic visualization of that field with kind of nice alpha blended lines. Okay. I'm like itchy. Everything's going wrong today. Here we go. Hope this pen works. So this is going to be part 1, which is just what is Perlin Noise? Welcome to a new multi-part series about Perlin Noise and creating a 2D Perlin Noise field, which you can visualize in a variety of ways. Eventually, maybe we'll make a nice rainbow-colored one. So ultimately, at the end of this video series, which is going to be 2 or 3 short videos, I want to show you how to make this particular project. But before I can get there, I just want to answer the question in this video, what is Perlin Noise, and do a quick P5.js JavaScript sketch that shows you the basics of it. So let me come over here and make a little diagram. So there are 2 functions in the P5.js library. This is also in processing as well. There are more than 2 functions, but there's 2 functions that I'm thinking of right now that are relevant to this discussion. One function is called random. Another function is called noise. Now, this is a little bit confusing because in truth, the word noise really just means random. If you think about audio noise, that sound, right? It's kind of like random audio gibberish. But the noise function in both processing and P5.js refers to a particular kind of noise called Perlin Noise. Now, Perlin Noise is named for a computer scientist named Ken Perlin, who was developing algorithms and has been developing algorithms for many years, but in particular in the 1980s for a film called Tron. Now, I'm not referring to whatever that recent one was called. I don't even know if it's recent anymore. Tron Legacy, I think, the original Tron from sometime in the 1980s. And one of the things that you might have noticed in computer-generated things that you experience is, maybe there is in the scene, there's like, to show my horrific artistic talent, there is like a vase sitting on a table. And at one point in computer graphics, there's this idea of a texture. I should re-record this, but I'm going to keep going. There's this idea of a texture, right, which is kind of the stuff that is painted onto that 3-dimensional form. Now, at one point, computer animators had to hand make these textures if you wanted the vase to look like wood or marble. I don't know why you'd want a wood vase, but whatever. The point is, Perlin Noise was originally developed for procedural textures of objects. Meaning, how do I create, I could, as an artist, I could render some sort of like wood-like texture just with my pencil and paper and scan it, or use some fancy Photoshop Illustrator-like program, or I could have an algorithm that generates all the pixels to make that kind of texture. So that's what Perlin Noise was originally developed for, procedural textures for three-dimensional objects in computer graphics. Now, Ken Perlin actually won an Academy Award for that. I don't know why that's like my terrible drawing of an Oscar. That looks nothing like an Oscar for technical achievement. So that's kind of a little bit about backstory. Now, circling back, I mentioned there is a noise function and a random function. The noise function gives you Perlin noise values. So hold off on the idea of procedural textures. I have an eraser here. I'm going to come back to that in part 2 when I look at 2-dimensional Perlin noise. But in this particular video, I am just going to talk about 1-dimensional Perlin noise. So what do I mean by 1-dimensional? Let's think about numbers over in a single dimension. Let's just pretend for a moment that that dimension is time. It's a useful way of thinking about it. So this is the axis of time, getting very deep into philosophy here. This is an x-axis of time. Let's think about the random function. So let's say every 60 frames per second, right, like an animation, like a P5GS or processing sketch, I'm calling the random function. I'm going to get a random value over time. Random, 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 random. Okay, I can't pick random numbers because I'm a human being, but you can imagine I might be getting random numbers between 0 and 1 over time. So that's what and this will look like if I were to graph it like some kind of big mess. Now Perlin noise in one dimension has the same sort of idea. Let's say I want to get random numbers. Oh, this pen is terrible. I don't even know if you can read this. Time out. Pause this video. By the way, look at this craziness over here. Hey, anybody, did I get that history kind of right? I was kind of just doing that extemporaneously from the bowels of my mind. So give me some feedback if I got that about right. I'm going to go see if I can borrow a different whiteboard marker. I'll be right back. I'm muting my microphone just so you guys know. Okay, I'm back. Let's see here. Now I have this. Hold on, I'm just looking to see. If I have any other markers. Yes, we will be getting into the actual algorithm. I don't know. Did anybody, nobody's giving me any feedback, so I assume I got that history correct. Let's just see how this does for me. All right, this is going to be better for right now. This will get edited together. So over here, okay. Here we are. Okay, I'm back. I'm going to just keep going. Checking the chat. I think the history was accurate. Thank you, Oliver. Okay, so I'm going to, now I'm going to draw my Perlin noise graph. Okay, here we go. And let me cycle these cameras. Okay. Back with the new marker. Well, this isn't so great, but let's see how this does. So I'm going to draw now the x-axis of time in blue. I wish I had a pink one or a purple one. Those are my favorite colors, in case you were wondering, but I don't. And I want now, instead of random values, I want Perlin noise values over time. So I'm going to draw you sort of a visual approximation of what it might look like. Something like this. You know, so the idea here, and the idea here is that ultimately at its core, Perlin noise gives you smooth random numbers. What do I mean by smooth? I mean that a random number that you might pick at any point in time is related to the random number you might pick later, a moment later, or the random number you picked a moment before. Whereas so this is random, this is noise, Perlin noise that is. In the core random algorithm, the actual random algorithm itself, those numbers aren't related at all. You pick, like I'm picking random numbers between 0 and 10. 9, 2, 7, 6, 1, 9, 4, 8, 9, 2, 1, 3. I pick 9 a lot apparently. But with Perlin noise, I might pick numbers like this. 2, 3, 4, 3, 4, 5, 6, 5, 4, 5, 6, 7, 5, 6, 7, 5, 6, 7, 8, 9, 8, 7, 6. Boy, this is like Perlin noise performance art. I won't do it again, but that's what that was like. I'm going to do a whole separate video, which is me reading aloud Perlin noise values. I'm sure people want to watch that. Maybe I'll even sing them. Anyway, so you get the idea. That's the core difference. Now, that's how it works. Now, there's two more pieces I really want to get to here. One is, okay, I get it. I get the difference conceptually. How are these values generated? Well, actually, they're generated just ultimately, Perlin noise is just a lot of math on top of the actual random function itself. So let's look at this, and I'm going to grab a paper towel here, and I'm going to explain to you, with my best effort, how the actual Perlin Noise algorithm works underneath the hood. Now, Ken Perlin has revised the algorithm several times over the years. I don't know, several, 1 or 2 times, 3 times, who knows? And you can kind of, I'll try to post some links to different versions or update, but I'm going to give you kind of the basic gist of it. So let's go back to random. Let's say I'm going to pick random values over time to start with. And what I'm going to do is actually say, I'm going to pick them every 10 units of time, 10, 20, 30, 40. So I'm going to pick those random values with some amplitude between something like 0 and 100. These are all sort of made up values. So I pick a random number here, then I pick a random number here, then I pick a random number here, and then I pick a random number here. Now, the next thing I want to do is do an interpolation function. What is an interpolation function? Well, here are some numbers. Here's me interpolating between them. That's like linear interpolation, I think. I just draw a line between the values. But maybe I want to do something a little nicer, and one possibility of one kind of interpolation is called cosine interpolation, or sine interpolation probably, which means let me draw a nice curve between these values. So here is the start of my Perlin Noise function. And let's just pretend I also had to pick a value at 0, which let's say I picked this one. So now I'm going to do that again. This time, however, I'm going to pick those random values every 5 units of time. 5, 10, 15, 20, 25, 30, 35, I don't know why I'm right, 40. And instead of picking between 0 and 100, I'm just going to pick between 0 and 50. So let me pick random values. And now, just using like a random function, now I'm going to do this. Now let me do that one more time. And I'm going to pick them every 2.5 units of time. And I'm just going to go between 0 and 25. And now I'm going to just draw. It's going to be something like this. Now, what if I were to do this possibly 8 times, 16 times, 25 times, however many times I want. And each time I'm halving essentially the amount of time that passes before I pick a new random number, and I'm also halving that amplitude. Halving, is that a, I'm having it for lunch. But I'm halving it, I'm dividing it by half, whatever. What then if I take all of these and add them together? Now, I'm kind of going to lose my mind here really trying to do this visually accurately, but let's just say for right now, I'm going to take this graph and add it with this graph. I'm going to get something that looks like this. It has the essential, I'm adding these values together with these values. It has the same basic quality, right? It looks kind of like that original shape, but there's lots of little variations based on these little tiny variations. And this is essentially how Perlin Noise is calculated. And these, by the way, are known as octaves. So Perlin Noise is calculated over a number of octaves, and essentially it's a bunch of random waveforms. And those waveforms, their period and their amplitude change over those octaves and get added together. And in that sense, it has a fractal-like quality. You might have to go back and find some of my videos about fractals if that concept doesn't make sense to you. But fractal is this idea of self-similar shape, meaning at any zoom level, it's the same thing. And because we're getting sort of finer and finer detail as we go through these different octaves, if we were to zoom in here and blow that up, we might see something that looks something like this, almost like that original one. So Perlin Noise, this is really how it's calculated. Okay, I'm kind of almost done with this video because in the next video I'm just going to dive in and write code to sort of visualize how it works. But let's just make one more point here. Actually, you know what? I'm done with this video. This is the end of this first video, which is just kind of explaining the history of Perlin Noise and how the algorithm works. The next video I need to look at, okay, well, if this is how I'm getting the Perlin Noise values, how does that tie into the noise function? How do I call it? How do I get those values back? And how do I use them in code? Okay, this concludes this particular video, which may or may not have a variety of mistakes and confusing aspects to them, and you, the internet, will let me know. Thank you for watching. Okay, how did that go? Give me in the chat, please. I would love a little. Look at this crazy. Give me a little feedback here before I move on and do the next piece. Did that make sense? Should I go back and do that again? By the way, this is my musical example that I was. Ooh, it has a little clipping there. Did you notice that? This is something I was going to demonstrate soon enough, but playing a scale with code. Where is that? Here it is. Wait. Move on. Was I recording to disk? Yes. Can you say the 10 digits clearly for me and also how you pronounce a decimal point? Sure. 1, 2, wait, I should start with 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, point. I have a bad feeling what you're going to do with that, but I'm going to enjoy it. Okay, it was good. Okay, so I am going to move on. Whew, I'm going to stand in front of this fan for a second, cool myself off. I'm going to move on. Where are we? 11:47, and look at one-dimensional noise in the browser. Okay, I could do that again at the end of the this session. Okay, I hope that was new for some of you and that made sense, and also that I got it right. Thomas wants to know, have you ever learned C#, C++, or any of the C languages? Actually, I used to program a lot in C and a little bit in C++. I have not used C#, but I do hear that Unity is all the rage, and maybe I should get involved with that. Okay, here we go. 73 people are watching now. That's very exciting. I'm going to minimize this. I'm going to cycle the cameras. Welcome to part 2 of a multi-part series about Perlin Noise. Wait, I want some music. I don't know why I feel like I need music in this one. This is ridiculous. What am I doing? I don't need music. Never mind. Welcome to part 2 of a multi-part series about Perlin Noise, in which I eventually am going to build a simulation like this, which I don't know, looks like lots of hair or a river or something. Eventually it'll be rainbow colored, but I am talking about Perlin Noise, ultimately how to deal with multi-dimensional Perlin Noise and how to make some interesting, pretty graphics from that. So where I last left off, previously on Perlin Noise Explained, I was making a mess of this diagram trying to explain how Perlin Noise is calculated over multiple octaves. So what I next need to look at is how do I actually call the noise function in P5GS or processing and get values out of it and make use of those values. So one thing that is true is if you call the random function, random, you can give it a minimum and a maximum argument, meaning I want a random value between 0 and 50. If you give it just one argument, it'll always assume the minimum is 0. And anyway, there's a variety of ways we could think about that. But this is probably something, if you're watching this video, that's familiar to you. You might think that's the same thing to do with Perlin Noise, right? Okay, so I could get my crazy random values, or I could get my nice smooth random values. And when I want the crazy random values, I want to give a minimum and maximum. When I want the smooth values, I want to get the minimum and maximum. But there's a problem here. Because of the nature of how Perlin Noise is calculated, you need to give it a different argument. And that argument is, in my previous discussion, I talked about sort of thinking about the space of one-dimensional noise almost as a graph along an x-axis, and you can think of the x-axis as time. But we can also now take a moment to just think of this as the x-axis. And you'll see this of variables named in a lot of Perlin Noise examples as x off, because what you want to tell P5 or processing, or what you want to tell those environments is, I want the particular Perlin Noise value at this position along the x-axis. So let's actually go and do that. So I'm going to go look at this. I'm going to go over here, and I'm actually going to just go over to the JavaScript console. And I'm going to call, first of all, I'm going to call the random function, just so we can see that. So if I call the random function with no arguments, I get some random value between 0 and 1. If I call it with one argument, I'm going to get the value of I'm going to get a random value between 0 and 100. 21. Lucky 21. Now, incidentally, by the way, never mind. I was going to show you that if you give it, let's do this. If you give it an array, and I say random A, I will get a random value from that array. Nice to see, right? So let's refresh here. Now, let's call the noise function. Now, I got not a number. So noise cannot be called without an argument. So given my previous discussion, we might say, OK, well, what if I want a noise value between 0 and 100? You might think to do that. OK, I got 0.577. Let me call that again. Hey, I got 0.577 again. Huh? Let me call at 100.01. Look at that. I got a very similar number, but it's a little bit different. See how this number that I'm passing into noise is really like time. It's where am I along this x-axis? What's my offset along this kind of pre-calculated? In truth, it's not like there's this big array that's already calculated. There's a formula for doing it behind the scenes, but it's sort of this pre-existing set of values. So if I say I want the noise value at 100, I'm always going to get the very, very same value. Now, you'll also notice here that the number I got was 0.577. Let's try saying, let me get noise at 0. How about noise at 200? Notice the value is always a floating point value, and it doesn't seem to be greater than 1. It also seems to be clustering around 0.5. So noise values actually don't have a uniform distribution between, by the way, the range is between 0 and 1. They also don't have a uniform distribution, right? If I were to say to you, let's look at, let's say I want to pick random values between 0 and 1 over time. And over hours and hours and days and days and days, how often do I pick 0.5 versus I pick 0.75 versus I pick 0.05, right? I should get a uniform distribution for pure randomness. That's the nature of randomness. With Perlin Noise, you'll actually see that the values cluster around the mean or the center, 0.5. So the distribution looks more like this, which is like a bell curve or a normal distribution. That's another topic for another day, but sort of interesting to note that or point that out. OK, so there I am. This is what I'm doing. I'm getting those values. So let's now actually make the sketch do something. I'm going to create a variable. I'm going to call it x. I'm going to set it equal to 0. And actually, I don't know why I'm doing that. First thing I'm going to do is just draw a circle. I'm going to use the ellipse function. And I'm going to just change the size of this to 400 by 400. I'm going to draw the circle at the center of the window and make it like 24 pixel diameter. And let's just see that I have a circle there. There we go. See this circle here? Let's make that a little bit bigger. OK, and now, I don't know there's some extra nonsense here by accident. Let me get rid of that. OK. There you go. See that circle? There it is. Now, let's make a variable called x and set that equal to 200. There we go. Now, let's do something different. And let's set that x equal to a random width value. Now you can see every moment in time, I'm getting a random value. OK. Now, I want to instead have noise. So let me comment this out and say var x equals noise. And then I'm going to say noise at time 100, something random. Well, notice it's over here. No matter what you do, the noise function will always return values between 0 and 1. So one thing that I want to do is take the result of that function, which goes between 0 and 1, and map it between 0 and width. In truth, I could just multiply by width, because multiplying a number between 0 and 1 multiplies it by width, gives me a value between 0 and width. So now, if I refresh this, did I not hit save? I didn't hit save. There you go. You can see every time I refresh the page, the sketch creates a new set of Perlin noise values. So even though the values are fixed for that moment, if I say noise 100, I'm always going to get the same value over and over and over again. If I refresh the page, I'm going to get a different same value over and over and over again. Because the Perlin noise space is seeded, and P5JS is going to reseed it every time you refresh the sketch. And you can use the noise seed function to fix the seed, but that's a little bit of an aside here. Okay, so we're getting something, but the number isn't changing. Why? Because that number is the same all the time. So what I want to do is make this, instead of a fixed value 100, I want to call this something like x offset. I want a variable. What I want to do is I don't have my graph here anymore, but if this is my graph of Perlin noise, I want to move throughout the space. I could move forward or backward, I could move quickly, I could move slowly. I want to get new values every time through draw. So here, all I can do now is say x. I can say x offset here, and I can say x offset plus equals 0.01. So let me do that and refresh this, and you can see now, you can see how it's random, but it's smooth, right? This is now the difference between this. Now you're looking at Perlin noise values over time represented as an x position compared to random values over time represented as an x position. So see the difference. I'm not looking at that graph anymore. I'm just looking at a single value, but I'm looking at it each moment in time. So hopefully this gives you the idea of Perlin noise, of how Perlin noise works in the core level. I think what I'm going to do is I'm going to end this particular video, and the next video I'm actually just going to show you how to draw a graph of those values, which might be somewhat useful. Oh, I forgot. No, don't go. Stay with me, please. This is an addendum to this particular video, which is that I kind of forgot to mention something important, which is I picked this number 0.01 somewhat out of a hat. And this number really means something. It was really a vital, crucial number in how the values will behave. So let's look at this sketch again and look at how it's behaving. Let's think about this graph up here that I probably has a lot of glare that you can't barely see. But think about how it might be to jump ahead really quickly or to move really slowly. And you can almost think about that as the speed of this thing, right? How quickly are you getting those new values? So for example, if I were to change this to 0.001 and refresh the page, you can see it's like moving very, very slowly because it's taking a lot of time to slowly walk through that Perlin noise graph. But if I were to change it to 0.1 and hit refresh, you can see it's moving much more quickly. If I were to make that number very large, like really large, if I were to say it's like 100, this is essentially just like randomness now, because it's moving so far ahead in that Perlin noise space that idea of the values being tied to the previous one or the next one is almost lost because you're jumping so far ahead. However, it does look different than random, right? If I go back to random, because you'll notice the random values are getting further along to the edges. That has to do with that sort of uniform distribution of values as opposed to Perlin noise values, which tend to cluster around the center. Okay, so I'm going to do a little bit more with you in the next video just about one-dimensional Perlin noise before we move on to two-dimensional Perlin noise and looking at how you might make procedural textures of Perlin noise. Okay, do the y-axis too. I should do the y-axis. Shoot. How many addendums can I possibly have on a video? I have a little bit of a cold, so I need to blow my nose. Is this new? I'm just curious, how many of you in the chat is this like totally new for? You can, sorry, was that, I should mute my microphone before I blow my nose. Or is this review? I know a lot of you have probably, this is sort of a variation on videos that I made for the Cadenze course or previous Nature of Code videos. But I see someone saying it's me, which must mean it's new. Okay. All right, so let me come back and I think it would be useful to do the graph because Gregory says, I have read that chapter 20 times in Nature of Code. All right. So hopefully I'm not torturing you guys with this. It's noon, so I'm going to just keep moving here. my whiteboard situation is not good. Okay, here we go. Okay. Welcome to another Perlin Noise video. Whoops, no, start over, hold on. Yes. I'm going to do the y-axis in this particular video. I know what I'm going to do in this video. Welcome to another Perlin Noise video. I totally forgot what I was going to say. There's a comment in the chat that says, show us how to make the actual algorithm for Perlin Noise. That would be interesting to actually write the algorithm. I'm not prepared to do that today because I'm going to keep pushing forward to get this 2D flow field thing, which I think will be interesting. Okay. I feel like the issue with displaying it with respect to time is you can achieve a similar effect by integrating randomness. Yes, I think that's right. Oliver makes a great point. Okay, back with another video about Perlin Noise. So far I've got the basics of Perlin Noise, and what this particular sketch is doing is just tying the x position of a circle to Perlin Noise values over time. What I want to do in this video is show you two things. One is I want to add the y-axis just to sort of see what happens if I do that, and then also show you how to actually graph those values over time as opposed to just seeing sort of a single value over time, which may be useful, I think. So let's do that briefly. Okay, so what I'm going to do is I'm going to add, now what's really confusing here is that I kind of was about to type y off equals 0. And that's not really a good idea. Because in the next video, I'm actually going to look at two-dimensional Perlin Noise. What does it mean for Perlin Noise to exist in two-dimensional space? And in that sense, I'm really going to have an x offset and a y offset. I don't really have a y offset. Really what I have is I have a y value where I want the ellipse to be. So I could do this, right? And then put y here. Right? I'm just going to add a y value, which is also mapped to noise, and I could have that be mapped between 0 and height, and then draw the ellipse at x and y. So let's see what happens there. But you can see it's just moving now along the diagonal. Why is that? Because the x and y values are always equal. Because I am asking for, I think we're going to need a visual reference here. So I'm going to really attempt to get a nice, right? This is the graph of Perlin Noise. If I'm saying, hey, draw a circle at an x, y position and have the x value be tied to this part of noise and have the y value be tied to this part of noise, x and y are going to be equal, meaning in the canvas, if x and y are equal, it's somewhere along this diagonal. So what I want to do is I want to have x and y both be Perlin Noise values, but not be equal. So I could have an entirely other Perlin Noise space, one-dimensional space, and get the y values from that. Another thing I could do is I could just say, hey, let me just get the y values from some other part. Like I'll get the x values from here and I'll get the y values from over there. So in that sense, what I need are two x offsets. Like I want an x offset 1 that starts at 0 and an x offset 2 that starts somewhere else, like really far away. How about 10,000? And so I want the x value from one offset, the y value from another offset, and both of these, they move through Perlin Noise space. Eventually x off 1 is going to get all the way to 10,000, and you're going to see repeating values, but it's going to take so much time, and x offset 2 will be somewhere else, you'll never notice that. So let's look at this, and now you can see I have this kind of it's almost like wandering sporadic bee buzzing-like behavior. It's kind of nice, actually. I got to move the mouse out of the way. So I don't know. This is actually, I think this is a good moment to. Oh no, I don't have this prepared. Right? This is a visual representation of Perlin Noise and music. Okay.
Coding rainbow.
Okay. Anyway, so this is the idea. I forgot what I was doing because I was just so excited that I had a moment to do something weird. Anyway, so you get the idea. Now let's think about, it's kind of interesting. Oh, there's so much that I want to keep going with this. Like, what if I put the y values a little bit behind? But anyway, this gives you the basic idea. Now let's do one more thing in this particular video, and yes. So in the chat, a question is asked, and the question might be around: could you give two-dimensional arguments to noise? And I could do that, and I'm going to do that in a moment. And in fact, that's how I'm really going to deal with a two-dimensional space. But I'm showing you kind of a way of getting multiple kind of single values for two different parameters using two different parts of the noise space. I know that's confusing, but it will all become clear. Or if it doesn't become clear, then all I have to say to you is this, because I don't know. It's like, I have a cold, so nothing is going well. All right. Okay. It's very hot in here. Okay. So anyway, okay, I was going to graph the values now because I don't know what I should be edited out of this particular. All right, let's graph the values because I think that's going to be useful. Okay. So what I want to do is I'm going to comment some of this stuff out. And I am going to write now a little for loop. So what I want to do is I'm going to say var x, and I'm going to write var x equals 0, x is less than with, x plus plus. And I want to draw a, I'm just going to draw a point at x comma 200. And I'm going to say stroke 255. So now I'm going to go back to the sketch, and we see there's this line going across the middle. Why is there a line going across the middle? Because I have a loop for every single x value, draw a point there, all those points are next to each other, it looks like a line. So now what I want is I want this y value to not be Perlin Noise. I mean, I want it to be Perlin Noise. The heat, the 90-degree New York City heat. So first I'm going to say random height. Now look at this. Now I just got a whole lot of random crazy points everywhere. So first of all, I want to stop this animating for a second. So there's one way I can stop it from animating, which I can say no loop. So now I have a bunch of totally random points. And what I actually want to do here is I want to connect them. So I'm going to say begin shape, no stroke, no stroke, 255 and no fill. And then I'm going to say end shape. And I'm going to draw, I'm going to say vertex. Right? I forgot what I was doing. So if instead of drawing them as single points, if I say begin a shape, end a shape with a bunch of vertices, it's going to connect them all. So now I'm going to refresh this. And you can see this is what I was trying to draw for you on the board before. This is now essentially a graph of random values, a random value for each point x along the x-axis. And by the way, if I allow it to animate again, this is what you get, a lot of totally random values. New random values every frame, but I'm going to put that in. Now, what I want to do now is change those to Perlin Noise value. So really what's going on here is the y value is a random value. So instead of y being random, what I want now is to say y equals the result of the noise function. So first, let me just plug in one point of time like noise 0. And we can see, okay, first of all, where are all the values? Well, remember, I get a value between 0 and 1. So one thing I certainly need to do, again, is map that value. And you know what? I'm tired of mapping. It's going to be simple just to multiply this by height. So you can see, every time I refresh it, I get one value across. That's because as I move from pixel to pixel, I'm not moving through this noise space. I'm just staying at one point in time. So now what I want to do over here is I want to make this a variable. And I'm going to say x offset starts at 0, and then for each one of these y values, go up by some amount. And now you can see there, I'm in the wrong place. Okay, hold on. I'm going to re-record that. It'll get edited. So many things I could fix with editing, but where was I? Yeah, I was here. Nope. Oh yeah, here I was. That's where I was. I'm still in the wrong place. Yeah, okay. This is where I was here. Then I went over here. It's going to be magical, seamless transition. So now what I want to do is I want to add an x offset variable, start that at 0, get the noise value at x offset, and go up by some amount, like 0.02. And now when I refresh that, you can see there's my Perlin Noise graph. This is what Perlin Noise looks like when I graph it. Smooth randomness as compared to random. So you can really see the difference now. Now I want to do a few more things with this. There's a couple things I want to do. One is I just want to show you what happens when I change this particular parameter. So let me make this 0.01 instead of 0.02. And actually, let's do something. Oh, the other thing, let's loop it. So you can see I'm adding the loop back in. It's animating, but remember the Perlin noise values are fixed. So I'm always if x offset always starts at 0, I'm going to get the same values. So let me do something where I make an increment variable, and I say that's 0.01. So I'm going to increase by that increment variable. And now I can do things like say, what if increment is 1? You can see what that looks like. What if increment is 0.001? You can see how smooth that is. And I could easily tie this to a slider. That would be a nice thing to do. And you can see how the graph changes based on that increment value. Now there's another thing I could do to this, which I think would be kind of interesting. What if I want to kind of scan across the Perlin noise space? What if I don't always want x offset to start at 0? So in this case, I could say start equals 0, x offset equals start, and then I could say the start also changes by that increment. Now look at this. Now I'm sort of seeing, and this is basically exactly what I did. I have a terrain generator example which does this in 2 dimensions, which I recorded before I made this video, so things are a little strange and out of order. But you can go and find that if you look for a YouTube terrain generator. Schiffman, you can see but this is exactly what's happening now. This is a 1-dimensional terrain generator. I'm moving across this space, moving across the Perlin noise space over time. Boy, there's so many things I want to add to this. Let me think about it. Okay, one thing I think I should mention here, by the way, this kind of looks like it's like a waveform, right? Like a sine wave. I could easily, just by the way, change the noise function to sine. And notice what I get. I get a sine wave. Now, the one thing, the sine wave, unfortunately, the sine function gives me a value between -1 and 1. So what I really need to do is change the mapping, like add height divided by 2 and multiply by height divided by 2. And now you can see the sine wave. But interestingly enough, these algorithms work the same way. They're just functions that when you pass it a value that changes over time, give you a new value, whether it oscillates perfectly or it moves kind of randomly. So there's a lot of possibilities here. And in fact, you could add noise. I could also I could say noise x off, times 10 plus, y equals, how come that didn't work? I want to add, y is, maybe 10 isn't enough, times 100. Yeah, you can see now there's the sine wave with a lot of sort of randomness, a little bit of randomness thrown in. Because what I actually did, and it's not offset very well, let's actually make this correct. I'm going to show you while I'm here, right? Let's say I have a noise value, which is noise of x offset. Map the noise value between 0 and 1 to between -50 and 50. And then let me take a sine value, which is map the sine wave of x offset, which goes between -1 and 1 to between 0 and height. And then what I want to do is say that var y equals those 2 values added together. And now you can see I have the sine wave with a little bit of noise added. And this, by the way, if you took like letter forms and you wanted to make them appear a little bit like handwriting, you could add a little bit of Perlin noise just to the pads between those letter forms. So you can see there's a lot of interesting possibilities here. And I could kind of do the opposite. Like I could say, well, let me make noise the primary thing and make the sine wave just like a little something that adjusts the noise. And you can see now, I don't know if this is harder to see, but there's a little sine wave in there that's kind of adjusting the noise in a sort of perfect amount, I think, by the way that I changed that. So there's a lot that you could play with here. So I'm kind of messing around because I'm nearing the end of the point where what I ultimately want to do is look at then, this is all about noise in one dimension. I'm drawing this graph in two-dimensional space, but my values live in one dimension. Last thing I want to do is I want to look for the noise detail function. And I'm going to look at the reference. And let's just look at yeah, you know what? This video was over before I said last thing I want to do. Let me go back. It'll it'll be a cutoff weird at the end. I should do a separate video just about the noise detail function. So I'm going to say goodbye. This will be a weird edit cut. So in a moment, I'm almost ready to look at two-dimensional Perlin noise and what happens when we get to two-dimensional Perlin noise, but I want to briefly record one additional video, which will be next in this sequence, just looking at the noise detail function and how that, no. The noise detail function is going to make so much more sense once I already have the two-dimensional noise. So that was the end. So at some point it's going to have an awkward cutoff. Okay. Thanks for watching this video. I'm ready now in the next video to move from one-dimensional Perlin noise to two-dimensional Perlin noise, and I'll see you maybe in that video. Okay. Time out. I need a momentary break here for a second. Where's my... You know, I really should be doing is I should make an example that takes this function and like makes it like jiggle based on the volume of this music. But today's not my finest day here if it's cold. Okay, how's it going? How's this going so far for everybody? Any questions? Any comments? Complaints? Please feel free to let me know. It's getting very hot in here, but I want to, it's 12:20. I don't know why. Today turned into Perlin Noise Day. Somehow that happened. So the next thing I'm going to do, okay. So let me answer a couple questions here. Have you done Minecraft Java programming? I've looked into it. I would really like to do more of it. I haven't really had the time. But you're right. There's a lot of similar ideas here in how the procedural terrain is generated and what I'm talking about here. I mean, I think Minecraft is has its own sophisticated engine for how that works, but there's a lot of crossover concept-wise. Thomas asks, what's the difference between processing Java and Java? So I'm kind of doing something maybe a little bit new here, where I'm saying, sometimes I say processing Java, because I'm trying to emphasize the distinction between processing and P5JS. So over here is the icon. The bottom icon is for processing, which is this particular programming environment. And this particular programming environment has an API with functions like ellipse and function like rectangle and fill and stroke. But the language is actually Java. P5JS has the same sort of API with vertex, ellipse, all that sort of stuff, but the language is JavaScript and is therefore executed in the browser. this program is executed as a desktop application, as a Java application. So sometimes I'm saying processing Java just to emphasize I'm using the Java version of processing. The library and philosophy and sort of like spirit is processing, but the actual underlying language is Java. The reason why I also mention this is because you can actually also change this to Python. You can also change it to Android. And you can actually write the processing, I could say processing Python. So there's processing Python, there's processing Java, and there's P5.js. Now, processing Java and processing Python have exactly the same API. All the functions have the same names and the same signatures. P5.js, while has a lot of the same stuff as processing Java, is actually not a port. It's really a reimagining of processing for the web. So there's a lot of differences in how there's a lot of subtle differences in how the API works, and a lot of new functionality that's based on web functionality. Yeah, so it's tricky because processing Java used to be referred to as P5 for short, and then P5.js is a new framework and often is referred to as P5 for short. So I try to avoid. I think for me I'm saying processing when I mean Java processing, and P5 when I mean P5.js, just to get that taken care of. Okay, let me close this out, and let's find this particular sketch, run it again, and now, will I teach processing Python? Not very soon. You know, one of the things that I really would like to do, and I don't know to what it is, have guest presenters. You know, the amount, and I would love to invite, in particular, guest presenters who look different from me, frankly, to be honest, to be sort of vague about what I'm saying, but I mean with more diversity. And so I would, so maybe I'm gonna, I haven't really gotten together to do this, but I would like to invite people to come and make tutorials. They can own those tutorials for their own use. They can have those tutorials exist as part of my Coding Rainbow feed. To the extent that I'm monetizing any of this, word makes me so uncomfortable. I would certainly share that with them. And I'm thinking of some people that I know in the back of my head who are Python programmers. So that's something that I'm thinking about doing. If you live in the New York City area, if you are a woman or a person of color, I would like to invite you to come but really anybody is welcome, of course, to come and make tutorials in the studio. So I have some plans for that in the future, but I haven't really gotten it together to do that yet. Okay. All right, two-dimensional Perlin noise. That's coming next. First, I need to deal with this sort of whiteboard issue. Let's see. I'm going to wash it more cleanly. I'm over here. This should hopefully help, because I'm going to definitely need a diagram for the two-dimensional Perlin noise stuff. And then we also will have three-dimensional Perlin noise stuff. I'm sorry for some of you I'm aware who have watched me regularly, or there's a lot of today is probably review or stuff that you know already. This, I will say the reason why I'm doing this is this gets asked all the time. This has been just sort of more about Perlin noise and how it works, and building up to a 2D flow field has been requested a lot on Twitter and the like. So, okay. Striking Wolf asked, do you know functional programming? Yeah, that was my answer. That makes sense? Good. Glad we covered that. Yeah, functional programming I'm aware of. I do some functional programming in various ways, and as I get this fall, I'm planning on doing a lot more kind of JavaScript stuff with text and language and server-side programming, and there'll be more aspects to the sort of functional aspects of JavaScript programming in those. Okay, one more question. Prasenjit asks, the difference between processing.js versus P5.js. I've actually covered this quite a bit, and I should plug this for a second. If you're, I should just wait till the end to do this kind of stuff. But if you are interested, you can go to creativecodingpodcast.com. I recently was on the Creative Coding podcast. You can go and listen to the Creative Coding podcast. I think I discussed this a little bit, but very briefly, processing.js is a separate project that was created years ago by John Ressig, and then it was taken over by a group that actually, I think by a group that's part of the Mozilla Foundation, if I'm correct about the history of this. And processing.js is really a direct port of processing to JavaScript and actually has hooks in it to translate your processing code directly to JavaScript. So you can actually use processing.js without ever writing any JavaScript and just run it behind the scenes to convert your code. But P5.js is a processing foundation project that is a kind of a new framework that is meant for people to write native JavaScript in. John Ressig did also make jQuery, that is correct. Okay, let's see. let me go see if I can find. I'm going to look one more place for another marker. I'm going to mute my microphone. I forgot to put on music while I was away. All right, I'm just going to live with this marker. It's actually, maybe it looks a little bit better now. And, oh, no, here. Take over the channel. Okay, all right, so let me close this. Let me come back to, whoa, craziness. Hold on, we got some music. Okay, I'm just getting this back to where it was originally. And then I'm going to make a new. Perlin Noise 1. 2D. Whew. Okay. All right, everybody. 12:30. I'm trying my best here. I'm going to do 2-dimensional Perlin Noise, then 3-dimensional Perlin Noise, then make the flow field. Ah. Oh boy. It's going to happen though. Yeah, I realized I've kind of really. I backed up so far. I'm like, so many little things to get to. But anyway, here we go. Okay, so the song ended, which means I'm going to go into the next video. So let's cover 2-dimensional Perlin Noise. Okay. Okay, sorry, I'm spaced out for a second. Welcome. The time has come. It's come to move from one-dimensional Perlin noise, which I have a graph of here behind me from my previous video, to two-dimensional Perlin noise. So what does it mean for Perlin noise to exist in one dimension versus two dimensions? So let's come over here to the trusty whiteboard and let's take a look. So this is a graph of Perlin noise values in one dimension. The singular dimension being the x-axis. And in P5, or processing, we ask for a particular noise value at, I'm just going to start over. I guess I could edit that together, but sometimes it's easier just to do the same 2 minutes again rather than edit. Okay. Hello, the time has come to talk about, I'm excited, two-dimensional Perlin noise. I forgot what I was saying. Okay, one more time. Hello, the time has come to talk about two-dimensional Perlin noise. That is not two-dimensional Perlin noise. Right behind me over here is a visual representation of one-dimensional Perlin noise, a graph over time or over some sort of x-axis of noise value, Perlin noise values, of smooth random values. So what I want to talk about in this video, coming over here, is what does it mean for Perlin noise to suddenly be in two dimensions? So let me draw for you essentially what was happening in that sketch. So this is a graph of Perlin noise in one dimension. And we know that the noise function takes an input, which I called in my previous example, x off, meaning some sort of offset along the x-axis, and the function will return the particular value related to that x offset. So now, even though this is a two-dimensional board, and I am here with you in 3 dimensions. This is a visual representation of one-dimensional value, of values along one dimension. So now I need a visual representation of values in 2 dimensions. So what I'm going to do here is now draw you a grid. And this marker is failing me. Let's try the other side. I think I need to not have gravity in this space maybe. And then the ink wouldn't drip to the back. I'm trying to hold it up like this. I need one of those astronaut pens. Anyway, so this is now a two-dimensional grid. What if instead of a particular noise value, let me come back to this. I am going to Staples and I am buying a box of fresh whiteboard markers as soon as I finish making videos today. Noise. What if I say x off, comma, y off? What I'm saying here is give me a particular noise value at a particular x location and y location in this space. So in the same way that this looks like a bumpy terrain, but it's flattened, you could imagine this being a bumpy terrain that's coming out towards you. Right? There's all of these values. And so this particular value, this particular value is similar to the value that comes after it or the value that comes before it. This particular value is similar to all the values that surround it. Right? There's a difference between, again, this is a very a difficult thing to wrap one's head around. There's a difference between drawing stuff in 2 dimensions versus pulling values from 2 dimensions. But what I'm going to do now, I think, is try to demonstrate Perlin noise in 2 dimensions by doing the most literal visual representation of this. So what I'm going to do is, color every single pixel with a grayscale value according to a Perlin noise value. So let's make that happen. Hopefully that explained it somewhat. Now I'm coming back over here, and here we go. So let's do some stuff here. Let's actually. I'm gonna keep this increment variable. I'm gonna get rid of this start variable. And I'm gonna get rid of a lot of this stuff, actually, but I'm gonna keep this outer loop. What I'm actually going to do, and I could do this with pixels. Let's do it with pixels. So what I need to say, I'm going to make the canvas 200 by 200. And then I'm going to say load pixels here in draw. Now, the way that the pixel array works in P5GS is a little bit tricky. And I have an entire video dedicated to just that. So if you haven't used pixels before in P5GS, go find that video now and then come back. There'll be a link to it in the description of this video. But what I'm going to do here is I'm going to add 2 loops, one for the x values, one for the y values. And then I don't need begin shape and end shape. I don't need any of this stuff. I can actually get rid of so much stuff from this example. Then I'm going to say update pixels at the end. And now what I need to do is I need to calculate an index, which is x plus y times, this is what I cover in the other video, x plus y times width times 4. And then I want to say pixels, that index equals 255. And then that's the red value. This is the green value. This is the blue value. And I'm going to say plus 0 just so you see, plus 3. And this is the alpha value. So if I do this, I should just see, okay. So what just happened here? Something weird just happened. It so happens that my machine is actually a high density display. It's a Mac Retina screen. And so the way high density displays work is they actually pack 4 pixels in for every pixel. And I don't want to get lost in a discussion of that, but I can kind of fix this issue just by saying pixel density. I can turn off the sort of high densityness of the display by just saying pixel density 1 pixel per pixel. And now you can see, there we go. So let's look at this now. And let's say I say random. For each pixel, I'm going to give random value. I'm going to pick a brightness, which is a random value. R. What? Adam is auto-completing me like I'm a crazy person. Okay, so you can see, there we go. We've got, back in olden times, when you might have used something called a television, the telly, and you couldn't get your antenna to connect to anything, you would see this kind of noise, static, randomness. That's what it looks like. Every single pixel is is a random grayscale value between 0 and 255. It's making me feel crazy. So now what I want to do, you can see that there's no relationship between any pixel and the pixel next to it. And I could say no loop, just so we could take a closer look at this. And you can see it's zoomed in. You can see every pixel is just sort of a random value with no relationship. So now, what if I want to use Perlin Noise? So let's one-dimensional Perlin Noise for a second. What if I were just to say I have a variable called x off. And what I'm actually going to do for every pixel is take a noise value at x off and multiply it by 255. You can see now every single pixel gets a single noise value from time 0 in one-dimensional noise. Every single pixel now has this color. Now what if I start marching through the one-dimensional noise? And I were to say, okay, for every pixel, change x off by some amount. It's kind of interesting. I get this sort of like weird streak. Why do I get this weird, crazy streak? Well, let's think about it. First of all, why is it going down? Shouldn't it go across? Let's look at those loops again. The inner loop is the y loop. So actually, for every x, I'm doing all the y pixels. Let me move y to the outer loop. Look, those streaks are going across. What's happening here is that, and we can kind of zoom in here for a second, right? Every pixel is changing ever so slightly according to Perlin Noise. White to gray to gray. And then when it gets to the end, look at the color that's over here. It's hard for you to see, but the color that's over here just comes right back and picks up in the next row. So in the grid, right? If I have one-dimensional Perlin noise values, I'm getting a variety of continuously smooth numbers, but then the one that is here, it's similar not to what's above it. This one is similar to what's before and after, but has no relationship to what's below. So what I actually want to do is give Perlin noise. This is where I want to have the values. I don't want to visualize in 2 dimensions one-dimensional Perlin noise. I want to visualize 2-dimensional Perlin noise. So if I come over here now, and I were to say, let me also have a y offset. Now, this is a little bit strange. Now, where do I initialize these? So the y offset, right? If I'm looping like this, x offset is going up, 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 up. Then x offset should reset and y offset should go up by 1. Up, 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 up. X offset reset, y offset goes up by 1. So what I actually need to do is x offset needs to be initialized here. Because for every single row, I want to restart x offset back at 0. And then I want noise, of x offset, y offset, and then after every single row, after every single inner loop, I want the y offset to go up. And I forgot I have a variable called increment. So let me just add that in here. And I'm going to run this again. And now look what I've got here. I've got something that appears rather cloudy. Why? Because pixels are similar to the pixels around it. It's very much like blurring an image. Actually, if I took that random snow, that random static, and blurred it over and over, blur, 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 that's like that cosine interpolation function that I referred to all the way back about how the Perlin noise algorithm was generated in the first place. So a blur, this sort of blur convolution, I can't believe I'm using a technical jargon, this blur convolution meaning a way of like mixing pixels together, but this blur thing is very similar to sort of smoothing out that randomness, averaging. So I could do things, by the way, to like increment is 0.1. Oh, and it's not looping. So let me turn loop back on. And let me make the increment bigger. Right? You can see what that looks like with a bigger increment. There's more changes. I could make the increment something even smaller. And you can see how this sort of noise, this noise field appears. So this is a literal visualization of the two-dimensional Perlin noise values. And as you might imagine, you could take those values and map them to lots of other things, like bumpy terrain or a flow field, which is the thing that I'm ultimately going to get to in the next particular video. So hopefully this helps you understand a bit more about how the Perlin noise two-dimensional noise works. And I'm going to do some more with it in the next video to make a flow field. Okay. I do like Python. Danielle asks, but I don't use it very often. I'm just not used to using Python. Okay, how are we doing here? It's 12:45. I'm like melting in the heat. I'm gonna bring this fan a little bit closer to myself here. Okay. Oh my God, I've got to finish this today. I don't understand how this has taken it. Let's see. Okay, you want to see increment equals 10? Sure thing. That's increment equals 10. By the way, boy, it's getting some really crazy repeating patterns. That's weird. I'd be curious to investigate why that is. Yeah, you can see the repeating patterns. I wonder, I have to look into that. I wonder if there's a bug in P5 or if this would also happen in processing. But I did want to take a moment to look at the noiseDetail. Probably should have just done that in, let me look at the P5Js reference. So noiseDetail refers to, so slow. the number of octaves and the fall off factor. So hold on a second. Yeah, this is good to. And then what's the default? I think there was. Yeah, the default is 4, and the fall off factor default is probably 0.5. Yeah. Okay, great. Okay, so I am going to make a really short video that covers noise detail. Hold on. And then I'm going to do the flow field. Okay. 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 Everyone, let's take a moment to relax. Where am I? By everyone, I mean me. Okay. Yes. Okay. Oh, and then 3D. There's so much to cover. Okay. Here we go. And I think I might move into processing when I do the flow field. But let's see. Okay, here we go. Okay. This is a very short video as part of my sequence on Perlin Noise to talk about the noise detail function. Do you remember a time, sometime in history, like earlier maybe when watching a previous video, where I talked about how the Perlin Noise algorithm works itself? And I mentioned this idea of octaves, right? We start with an octave, and it's of random values that are smooth, and then we get another octave, and we pick. I'm gonna start over. Fall off is. I just realized I didn't like. Is fall off the value that's saying how the period should change, or the amplitude, or both? Yeah, I know. Let me look at the documentation. I'm just going to read the processing documentation for a second because that P5JS page is really slow. Contributing exactly half, starting at 50% strength. Fall off amount could be changed. Additional, each octave now have 75% impact. Okay. 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 Camera, thank you. Oh, sorry. I was just reading this documentation page to remember. And what you can't see is that I don't have a trash can in this room. So I just have this little, on the desk over here, I have this little pile of dirty tissues. Hold on, let me mute my microphone. I have a bad cold today. Which. Okay. Okay, here we go. Hold on. I hear that the class has broken up. I'm going to go see if I can grab a different marker because I think I can now. Hold on, be right back. Where's my soundboard? I lost my soundboard. Whatever. Can you hear me? Yes. I don't know. I need a like.
Goody power. Goody power.
Okay. Okay. All right. Okay, here we go. I'm going to do this. Remember I said I was going to make a really short video? It's going to be like an hour long. I'm the worst. Okay, here it comes. Hello, this is a video in my continuing series about Perlin Noise. And this one, it might be my world record shortest video ever. And when it's like 20 minutes long, you guys, at the end of this video, you can laugh at me. But I just want to cover briefly what the noise detail function does. And I don't know why I'm talking so fast. Let me start over. Oh my God, I don't know why I can't do this. Here it is. Okay. No, the pen, it's going to work. I don't need to check it. Hello, this is another video in my continuing series about Perlin Noise, and I just want to briefly show you what the noise detail function does. And if you can remember a time, a little while ago when I recorded my first video today, or I don't know when you're, what? Never mind about time. Time doesn't exist in the world of YouTube. But I do have a previous video which you might have watched where I talk about how the noise algorithm actually works. And if you recall, there was this idea, oh, look, it's a purple pen. It's so exciting. I didn't even know what color this was. There was this idea of picking random values spaced apart with some amplitude and then interpolating between them. And then, again, picking random values spaced closer together with a smaller amplitude, and then again picking random values closer together with an even smaller amplitude, and then interpolating between those. And then adding all of these random waves together results in some nice Perlin noise. This is how the Perlin noise algorithm works. Now, over here, we have a visualization of Perlin noise in 2 dimensions, which I just talked about in my previous video. Smooth randomness, each pixel having a similar grayscale value to the pixels around it. Now, what we can actually, so this is the default visualization of 2-dimensional Perlin noise, but we can look at how that changes based on this noise detail function. So what the noise detail function does is it actually takes 2 arguments. Let's say I say noise detail 4. And I'm going to make this a little bit bigger. You can see nothing changed. Can you see? But if I say noise detail 8, you can see that it changed. Look, it's got finer detail. Noise detail 24. Can you see that even finer detail? So what that first argument is doing is controlling the number of octaves. So the more octaves that you have, the further kind of down this trajectory you're going and the smaller, more fine detail you're getting. Now, over here, I kind of want to, okay, now, let's go back to noise detail 4. That's the default. There's also a second, and by the way, if I were to say noise detail 1, like what if I just do 1 octave? You can see now we've kind of lost that finer detail and just have this sort of smooth grayscale values. Now, what if we look at the second argument? The second argument is often referred to as fall off. Remember I was saying how the period of these waves is shrinking, the amplitude is shrinking? Well, by what factor? It's shrinking by a factor of 0.5, half. So if I were to say noise detail 4, 0.5, hold on, I don't like the size of my things here. You can see that's the sort of default noise. But I can now say noise detail 4, 0.9, and look what that looks like. A little bit weird. Or 0.2, and look what that looks like. Or I could say 0.4, but with 12 octaves. You can control the quality of the Perlin noise. I actually am curious, just for a second, to look at, what it looks like with this 1-dimensional Perlin noise example. Let's just change the noise detail to 1. Time out! Remember I said this was going to be a short video? Why did that not work? Why does it not know what noise detail is here in the console? Oh, I don't know why that didn't work. Okay. Splice back in, weird edit. I'm just going to start right into it because I don't think there's... Okay. Let's try noise detail 1. You can see how this graph really changes. You sort of lost the sort of finer detail, and it looks, you only have that kind of like original random noise. Now, if I say noise detail 8, you can see how there is even more detail in the sort of finer points of change. And I could also say now noise detail 8 and then change the fall off to 0.2, and you can see what that looks like versus 0.8, and you can see what that looks like. So there's a lot of how you alter the noise detail function can change the behavior of the noise, and that's something you can control to get a variety of different effects, whether it's pixel effects or otherwise. Okay, that's finished now. Okay, I want to finish for the day, but it's because it's 1 o'clock. Let's see, how long is this live stream? I haven't even hit 2 hours yet. I don't know what I'm complaining about. It's just been 1 hour and 45 minutes. There probably is a noise detail max, but I don't know. Okay, so what I want to do now is the flow field. Am I really going to do this from scratch? I'm tempted to do this in processing now because it'll be much easier to do this whole thing. Okay. What a day this has been. Okay. Hold on, let me put on some music for you guys while I get myself set up here. Okay. Mine is completely dead. Okay. Okay, I think I'm ready. I'm turning up the fan for a moment. I don't know if this is blowing out your ears, just to cool off for a second. Hello! Okay, this is going to be it for today. I've decided what I'm going to do. Let me turn off the music. I decided what I'm going to do is now basically do a coding challenge, which is, Striking Wolf 2012 mentions if I do the flow field in P5, the performance is going to be hellish. And it is a very good point. And yet, I'm going to do it anyway. Maybe I shouldn't, though. Should I do it? Because, hold on, it's not that bad. It's going to be fine. I'm going to do it anyway. So what I'm going to do is now this is going to be it. It's 1 o'clock. This is probably going to take anywhere between 10 minutes and a half an hour. I'm going to just start from this example. And I'm going to finish. Hold on, I'm going to close a lot of other stuff that's unnecessary. I don't need that. There's cooking going on behind me. I smell something delicious. My goal is to end with this. Now, I won't be able to do it as high resolution with as much speed, but that's going to be my goal. So let me go now and I'm going to now open this in Atom. You know, I can always just do stuff low resolution if need be. Okay, as long as I use variables, I can change correctly, I can change the resolution whenever I want. So, okay, hold on. So here it comes. This is going to be I'm going to try to make this good. So I think that other stuff will just go in a playlist about Perlin Noise. And then this video that I'm about to do will go in the coding challenge. Will go in the coding challenges playlist. So this is going to be, so I'm not going to start from scratch. I'm going to start from the two-dimensional Perlin Noise example. Okay. OpenCL. Okay, here we go, everybody. Here comes cycle the cameras. Gotta fix this camera. Here we go. Funky chicken. Funky chicken. Funky chicken. Okay. Okay. Here we go. This is gonna happen. This is gonna happen now. Okay. I gotta get good fan placement. Good fan placement. Okay. Here we go. Ah, there's a cool air. Okay. Here we go. Hello and welcome to another coding challenge. In this coding challenge, I'm going to program a visualization that looks just like this. Streaky, hairy, like... No, I don't want to say... That just sounds... Streaky, hairy was just like a not a good way to start. Okay. Hello and welcome to another coding challenge. In this coding challenge, I'm going to program a visualization that looks just like this. That was for the thumbnail. And I'm going to do it in P5.js using JavaScript in the browser. What's running over here is an example that I made previously in processing, which will give you higher performance. So at the end of this video, perhaps I'll take a look at that very briefly. So I'm not going to start from scratch. This video is really going to be built on top of this idea of two-dimensional Perlin Noise. If two-dimensional Perlin Noise is not familiar to you, stop now, go to the video description, and go and find my series about Perlin Noise, and then come back. Okay, hi, you're back. Great. Okay, let's get started. So I'm going to start from this particular piece of code, which generates this particular output. So this is already an example with two-dimensional Perlin Noise, and each pixel gets a grayscale value according to two-dimensional Perlin Noise. But I want to do something different. What I want to do is, in the kind of grid of pixels, right? This is my very, very low resolution grid of pixels. Instead of having a grayscale value for each pixel, so to speak, what I want to have is a vector. I want to have an arrow pointing in some direction, and I want that direction to be a direction set according to Perlin noise. Because ultimately what I'm going to do is I'm just going to like pour a whole lot of particles into this area, which is known as a flow field. This is known as a flow field, and I pour the particles in, and they're going to follow the arrows, and we'll see what happens. Okay, so the first thing that I need to do is start revising the code to make vectors instead of pixels. So let's take a look at how that might work. So I'm going to work with a very low resolution canvas, just 200 by 200, just to kind of get things kind of started here. And one thing that I also need to think about as a core variable here is I need to think about what is the ratio of kind of cell to width. So I don't want to have an arrow for every pixel. It's going to be unreasonable for me to have 200 vectors. Instead, maybe I want a vector every 10 pixels or every 20 pixels. So let's make that a variable called like scale. I'm going to call it SCL, short for scale, and I'm going to say that's 20. And then what I also need to have is columns and rows. So I'm going to have, the columns is going to be the width divided by scale, and I better floor that. Floor is something that gets rid of the decimal place. And I'm going to say rows is height divided by scale. So now what I want to do is I'm not dealing with pixels anymore. So I can get rid of load pixels. I can get rid of update pixels. And in fact, I can get rid of all this pixel array stuff. But let's just see that things are working for a second. So what I want to do is have y now go through all of the rows and have x go through all of the columns. And what I want to do is I'm going to draw a rectangle. I'm going to draw a rectangle at x times scale. I got to scale up, y times scale, and the size of that rectangle is scale. And I'm just going to give it a random fill for right now. And I want to see that I'm at least getting a grid of rectangles. So if I run this, okay, so this is working. So this is now going to be my grid. Now, what I've done is I put a grayscale value, a random grayscale value in every cell. Hey, why don't we make that a random noise value just to get started here? So let me now change this. Look, I already have this here. I already have this noise function. Why not? Let's just make that fill based on that noise function. And you can see, okay, so you can see right now that I'm not really, because I'm so low resolution, that these cells aren't, these cells are kind of like the color is almost identical. So one thing I'll do, let's just try making the scale 10. You can see, let's make the increment a little bit bigger. There we go. So now we're starting to see something that looks a little bit more like Perlin noise. And one thing I want to do also, just while I'm working on this, I think it would be useful to just keep an eye on the frame rate. So I'm going to do something a little bit goofy. I'm going to make a variable called fr. And I'm going to say fr equals create p. So I'm making a paragraph element on the page. And then I'm going to say fr HTML frame rate. And I'm going to floor that. So this is a p5 function that just gives me back the the frame rate. I want to just see it as a paragraph element on the page. So you can see the frame rate, right now everything's fine. I'm running really fast, like 60 frames per second. So, okay, so this is my grid, and I essentially have a grayscale value for every spot on the grid. But that's not what I want. What I want is a vector for every spot on the grid. Okay, so one thing I could do is, instead of saying fill, let's at least right here create that, create a vector. So what I'm going to do is I'm going to say var v equals create vector. Now actually, there's actually a function in P5 where you can create a vector from an angle. P5 vector from angle, and I'm going to create a vector from the angle 0. I'm really sorry, but I have a cold today, and I have to blow my nose. If Mathieu wants to edit the blowing the nose out of this video, I'll appreciate it, but it doesn't have to be. It might just be in the video. Okay. Back from blowing my nose. I now have a vector. I've created a vector from an angle. And what I want to do actually is, instead of drawing a rectangle, I'm going to say stroke 0 I'm going to draw that vector as a line. So I'm going to say push, pop. There's a bunch of different ways I could do this, but I'm going to rotate by that vector's heading, and then I'm going to draw a line from, so I'm going to translate to x times scale, y times scale, and then I'm going to draw a line at that spot. That's a line from 0, 0 to scale 0. So what am I doing here? What I'm doing is I'm saying for every single one of those vectors, translate to this spot, then draw a line that's just a line like this, and then rotate it according to the heading of that random vector, the angle, so to speak. So now, if I run this, you can see, look, I have a whole bunch of lines pointing directly across. Now, what if I were to say from angle pi divided by 2? Now I have a whole lot of lines pointing down. What if I were to say pi divided by 6? Now I have a whole bunch of lines pointing that way. We're getting somewhere, right? You see where I'm getting at? Because what I can do now is I could say, what if I have a random angle between 0 and 2 pi? Oh, okay, first of all, I should probably clear the background. So you can see now this is just a random vector for every spot in that grid, every frame. So one way I could stop it from like changing all the time is I could say a random seed 10. So if I reset the random seed, you can see this is a whole bunch of random vectors. Now, ultimately what I want to do is show you how to make this field of vectors, this flow field, with noise values. But I could come up with other ideas. I could use sine waves. I could get a data input. Ooh, I could get like wind data from various geolocations through some kind of like weather API. And there's a great project, which I've shown in other videos, which does that. But I'm going to just use Perlin Noise. So let's go back and say the angle is the noise value times 2 pi, right? So when I wanted to get a grayscale value between 0 and 255, I took the noise value times 255. Now I want a random angle. I want the noise value times 2 pi. I don't need the random seed anymore. From angle, that particular angle, and now you can see, there we go. So now I have this nice flow field, essentially, of all of these vectors kind of pointing similarly, and each time I refresh, I'm going to get a slightly different one. Now, one thing you might notice is that I don't actually need to calculate this every time through draw, because ultimately, I don't need to calculate this every time through draw because ultimately it's staying the same. I could calculate it once in setup and then refer back to it later. However, I think this might be a good time. You and me, okay, we need to talk. Meet me over here at this other camera. We need to talk. Actually, never mind. Let's talk over here. There is Perlin Noise. I've shown you one-dimensional Perlin Noise. Lo, I've shown you two-dimensional Perlin Noise. I have yet to show you three-dimensional Perlin Noise, and in fact, Perlin Noise can exist in any n dimensions. But here is an opportunity where we might decide, let's do something with three-dimensional Perlin Noise. So the one dimension is the x-axis. Another dimension is the y-axis. Imagine a z-dimension as slices. These angles change as slices that are like coming out of the screen. Well, what if instead of actually building something visually in 3D, that we thought of that third dimension as time, every frame of animation? What if I were to add as a global variable z off and set that equal to 0? And then I were to say noise x off, comma y off, comma z off. I've now said give me noise values in three-dimensional space. So there's a noise value right here in three-dimensional space. It's similar to all the values that surround it. And so I'm looking at a slice of noise values. Then I want to present another slice of noise values. Then I want to present another slice of noise values. So those z offset change every time through draw. Can you hear people laughing and talking in the background? I don't know if you can. And now, whoa, it's changing like crazy. So I'm moving through time a little bit too quickly. So let me move like quite a bit slower. And let me move even slower. So you can see now I have a flow field that's actually changing over time. And you can imagine there's lots that I could do just with this much. But ultimately what I want to do, if you recall, and we can sort of see this crazy sketch now is like really just like filled over itself a zillion times. But what I'm trying to do is recreate this particular visual. So what's happening in this particular visual is that particles are being dropped on top of this flow field and following those arrows. So this is the first thing that we need to do. Now, I just realized we have a bit of a problem, small crisis of conscience here, which is that if I want to drop a particle on there, I need like a whole like physics engine and to move the particle around and all that. And I kind of want to just go and grab, let's make it. We can do this really fast. This is a coding challenge. I'm going to add the particle object from scratch here. So what I'm going to do is I'm going to make a new file. I'm going to call it particle.js. And I'm going to use a JavaScript constructor function. And my particle needs to have a position, which I'm going to just make it 0, 0. It needs to have a velocity, which is going to be an 0, 0 vector. And it needs to have an acceleration. I'm going to write an update function where the position gets added the velocity, and the velocity, the acceleration gets added to the position. If you're confused about how these physics engine works, go and watch all of my Nature of Code videos on physics engines. And then I'm also going to reset the acceleration to 0 by multiplying the vector by 0. Then I'm going to write an apply force function, which is a function that receives a force. And what do I want to do with that force? I just want to add it to the acceleration. So this is actually all I need. Well, this is so easy. And then I just need a show function. Whoops, I wrote that incorrectly. Equals function. Then I want a show function, which, what does it do? It draws the particle. So what should I draw it as? Let's just draw it as a point for right now. We're going to say stroke 0, point, this dot position dot x, this dot position dot y. So this is nice. I have this really simple particle object. It has position, velocity, acceleration. It has a little update method to update its velocity based on acceleration, to update its position based on the velocity, and then has an apply force function to accumulate any forces into the acceleration. So now I just need to make sure that my index.html file references that new particle.js file. And let's just very, very quickly make a particle array. And in the particle array, I'm going to say particle index 0 equals a new particle. I've lost my train of thought here. A new particle. New particle. And then I want to say here, particle index 0 dot show. Sorry. And dot update. And let's just see. OK, what's missing? Couldn't find particle.js because I typed that in wrong. I said particles.js, whereas the file is called particle.js. And now particle is not defined. Particles. And this is also very confusing here. The array is called particles. There we go. So you can see there's that particle up there in the corner. So I have one single particle. That's good. Now what I want to do is add a whole bunch of particles. Let me make this a for loop. It's less than 100. Let's add 100 particles. And just say particles index I. And then let's write another for loop, iterating over the entire length of the array. And having each particle. OK, so now particle, I typed something wrong, particles. Okay, there should be 100 particles there. Let's make sure all the particles are everywhere. Let's give the particles random positions to start. So you can see there's 100 particles around randomly. And then, just to make sure they're like doing something, let's say p5 vector dot random. So this gives them all a random velocity. Okay, so the particles are moving around with a random velocity. They're doing something. Okay, one thing I need to do, I just realized, is that I need to have the particles wrap around. When they get to an edge, they should come back on the screen. So let me add that really quickly. So I'm just going to add a function called edges. And I'm going to say if this.pos.x is greater than width, this.pos.x equals 0. And I'm going to do this in a kind of shorthandy way. And I'm going to say less than 0 should equal width. And then I want this again, but I want to do it with y. And I want this to be height. And I want to do this then needs to be y. And this should also be height. So I now have a new edges function. And I can quickly also say, wrap them around the edges here. So now we should see I have a whole lot of particles moving around forever and ever and ever. And let's not render the vectors for a second. OK, so now I have a window with a lot of particles moving around. But I want those particles now to be affected by the actual vectors in the flow field itself. So how do I do that? OK, this is the crux of this project. So first thing I want to do is I want to actually say, I want to give these like quite a bit of alpha. So let's see if, so you can see it's slowing down quite a bit, but I'm drawing the vectors, but you can see the particles are not moving anywhere according to the vectors. I also, just while we get started, I'm going to take off z offset to see now this, oh, whoa, did I not hit save? Yeah, so now I want to make sure this works with a fixed flow field. And with the particles, I also, just so we see them a little bit better, I'm going to say stroke weight 4 to make them a little bit thicker. Okay? Oh boy, but I don't want my vectors to have that stroke weight, so I'm going to say stroke weight 1. Okay, so now we can see the particles moving and the flow field kind of behind it. So what I want to do is say, for every particle's location, look up the vector that's nearest to it, and then apply that as a force. So here's the thing. All of the vectors are calculated up here. So what I want to do is actually store all of those in an array. So I'm going to make a variable called flow field, which is an array. And that array should have as many spots as there are columns and rows. So now what I want to do is say flow field equals a new array. This is a weird thing to do in JavaScript, but I'll do it anyway. You can actually preset the size of an array by saying new array. And maybe that was a bit unnecessary, but I'm going to do that anyway. And then what I'm going to do here is I actually already have perfectly the calculation. This was left over from my pixel example. This should be columns, and this should not be multiplied by 4 anymore because I don't have RGB values. I have a single value. I can now say flow field index equals that particular vector. So now all of these vectors that I'm calculating are now stored in that particular array. So now what I need to do down here is say, I'm going to say particles index I, and I'm going to write a function called follow, and I'm going to pass in that flow field. So what I'm doing is I'm saying, hey, you particles, here's an array of vectors. Each particle is responsible for finding the appropriate vector in that array to look up. So for example, just to come back to this diagram, I'm a particle right, let me get my, actually it's fine to use it. I'm a particle right here. My position might be like 300 by 200. And maybe these are 100 by 200. I need to first divide by scale to look up the appropriate index into that array, find the vector, and then apply it as a force. Let's see how that works. So if I go to the particle function, I'm going to write a new particle object, the constructor function. I'm going to write a function called follow equals a function. I'm going to just call this vectors. And now what I'm going to do is I'm going to say x equals floor, this dot position dot x divided by scale. So I need to take, remember its x position is its actual place on the screen, but its corresponding position in the grid, I have to scale down by that scale variable. Its y value is do that with y. Then the index is x plus y times columns. This is that formula for how you take a two-dimensional value into a one-dimensional array. And I cover that in some other videos, which I'll try to link to in this one. And then, now I should say the force is that array of vectors at that index. And I should be able to say this dot apply force, that force. So now essentially what I'm doing is I'm saying, based on I'm a particle. Based on my xy position, scale myself to a grid of column and rows, then look up the corresponding vector in that one-dimensional array, and then take that vector and apply it as a force. So let's now actually have the velocities start at 0, and let's see if this works. And I'm sure I missed something, but let's give it a try. Oh, okay, that's kind of working. But you can see, excuse me, that they're spiraling out of control in terms of speed. So one thing I should think about is, okay, I should think about, one thing I should really think about, is what is the magnitude of these vectors? So maybe these vectors, I need to set their magnitude to something much smaller, like 0.1. They shouldn't really be that strong, like a full unit, and you can see that now, but you can see they're still like really speeding up over time. That's because this acceleration is just building up and pushing and pushing. There's no limits to how fast these particular particles can go. So I think something I could do here, which would make sense, would be to have a maximum speed variable and set that equal to like 4. And then in the update function, I could just say this dot velocity dot limit, this dot maximum speed. So now I'm just saying the particles actually, no matter how much you start pushing them, they do have an ultimate maximum speed. And now we should see that the particles are following this flow field. And maybe they're not following it, and I could kind of control what that, now I could go back and I could say, well, actually, maybe I want the magnitude to be 5. And you can see when the magnitude is 5, they're going to be lockstep exactly with the flow field. So you can see what the magnitude of that force is really controls how exact they are in terms of following this path. And by the way, let's add the z offset back in so those vectors change over time. And you can see now what we're kind of getting. We've got these particles following a flow field, but that flow field is changing over time. Reasonably, I've still got 30 frames per second. I'm going to do a couple more things. One is let's add some more particles. Let's have z change a little bit more slowly. Something like this. And let's see how we're doing. So now I have a lot more particles, but it is running rather slow. So one thing I could do here, hopefully to get it to run quite a bit faster, is I can actually just not bother to draw the vectors. The data for the vectors is still calculated and exists, but I could skip drawing them. And you can see now I'm getting a nice 60 frames per second. It's really getting stuck at the top and the bottom. That force is really quite strong. So I'm trying to, I set the magnitude to 5. Let's set it to like 1. And actually I'm going to set it to 0.05. Anyway, you could play with this to your own. I could also, one thing that I could really think about is, well, do I want the full, maybe I want the vectors actually to have more variety to them. It's generally always pointing to the left, because remember I'm picking random values between 0 and pi, and they cluster around the middle. So I'm not picking random. So like I could say times 2 pi times 4. And now I'm going to get a lot more of sort of like noisiness. But there's a lot of different ways, and it's all moving like kind of too fast. And I should create some sliders, and I can kind of like really control this stuff a little bit more strongly. So you can see this is more what I was trying to get. So I have a sort of stronger flow field, but there's a lot more variety in terms of where the particles go. Now I could add some separation so that they don't get on top of each other as much, but you get the idea here. Now, what's this? I basically have all the way done. I now have this flow field where I can drop particles in it, and I could sort of push the performance here and say like, well, what if I try to drop, 500 particles in? You can see it's running a little bit slower, but I've got more stuff happening. But what if instead of drawing the particles as dots, what if I drew them? What if I allowed them to blend their alpha, to be sort of like alpha blended across the screen for a while? So let me to kind of create that visualization. So really now, one thing, if I were you, I would stop this video and just go to this show function and play. Make rainbow colors, add alpha values, but let me do a couple things to try to get that effect. So one thing, I'm going to return the stroke weight back to 1, and I'm going to give it quite a bit of alpha, and in the sketch, I'm also going to draw the background now only once in setup. So let's see what we get here with this. So now you can start to see what I'm getting here. I'm getting this kind of nice alpha blendy pattern. Now, if I were to zoom into this, you can see there's actually like the particles move faster than 1 pixel per frame. So they're actually skipping pixels. So something that could actually be quite useful here would be to have each particle store, at the very least, a previous position, which I'm going to say is, to start with, is a copy of its original position. So when it starts, it has its current position and its previous position. And then every time it moves, right after update, actually, let's do this. Every time after so what I want to do is actually not draw a point, but I want to draw a line from its current position. And I know that camera just went off because that means a half an hour has passed. To its previous position. This dot previous position dot y. Now if I'm in the wrong place. If I run this again, okay, there's a couple issues. Number one is, oh my goodness, what is going on? There's some crazy extra lines. So we have a problem, right? Because, I put a fan there. Okay, we have a problem. Come back to me. Coughing, cold. Edit my tripping and coughing out maybe, right? If I'm always taking a particle and drawing a line between its position and its previous position, when it leaves, its previous position is here, its new position is here, suddenly this line goes all the way across. So I want to add an extra check in here just to correct that. There might be like a better way of doing this. And actually what I could do is I could just update it in this edges function, which actually, let me do that. This is different than how I did in my other example. But what I'm going to do in this edges function is I have to add, right, if any of these are true, what I need to do is say what? I want to say this dot previous position dot x equals this dot position dot x. So I'm gonna write a function. This dot update previous is a function which just does this algorithm in it. Whoops, x. So anytime it hits the edge, I'm going to just update the previous. So this is like an extra time. And I need to make sure I do this then right before I draw it. So I actually want to have edges right before show so it gets updated. And then so this should correct that problem. So now you can see, oh, look at that. Okay, so it's actually it's doing something interesting. I never update the previous position, so it's actually drawing a line from where it started to its current position. So let me actually add the most crucial part here, which is that I also want to, every time after I draw it, to say this.update previous. So after I draw it, the previous position becomes the current position, and now you can see what this is doing, and I'm getting nice continuous lines. I don't actually see those continuous lines. What did I miss here? Hold on. Time out. I'm going to debug. What did I do wrong here? Because this should be right, because I draw the line, then I move it, and the line goes from, hold on. Let me do something here. It's so hard to tell. Let me have its maximum speed be like 20. And hold on. And its stroke be 0. And the background. Oh no, it's working. So you can see it's drawing as lines, not points. So I didn't need to debug it. It is working. It's drawing on top of itself because it's the way that I'm probably updating it is a little bit awkward. So hold on, let me go back. I don't know if anyone's paying attention to this anymore. Let me put background back in setup. And give this some alpha. All right, let me think about this. It draws a line. Let's think about this. It draws a line from here to there, and then it moves, and then it draws a line again from. So this gets layered twice, which is why I'm seeing a little bit of an extra dot. I don't know of a great way around that, but I'm not going to worry about that right now. And let me make the maximum speed like 4. And you can see what we're getting here. So I wonder, I'm just curious. Okay, so. Okay, I'm back. I didn't actually need to debug anything. It is working. So you can see I've basically gotten the gist by programming from scratch of this particular example. Now, there's a few things that are different. Number one is in this larger version, one is I've got kind of higher resolution going on. One thing that I think you probably would notice is this is running reasonably at 30 frames per second. But if I were to go back and try to add, to make this run over like a much larger canvas and have something like 2,500 particles, you're going to see that currently it's running at like 4 or 5 frames per second. Whereas this processing version, which I will pull up right now, this processing has 10,000 particles. And it's, for whatever reason, it's 1,200 by 800. Now let's look at, and actually I'm going to render this with, in the P2D renderer, which uses OpenGL hardware acceleration. I'm going to print the frame rate just to the console and take a look at that. Come alive, processing. So we can see that this is actually running over 50 frames per second. And once again, let me point out, there are 10,000 particles and I'm at kind of high resolution. Whereas here I have, I'm only 1,500 and not as high resolution and it's running really, really slow. So what I would need to do to pull the most performance out of the web browser would be to probably render this somehow with WebGL in a kind of hardware accelerated way, which maybe I'll continue and look at some point. But hopefully this video gives you the basic idea. And what I would love to see, and I'm just going to, what I'd love to see you do is first of all, make this like rainbow colored. Try playing with the various parameters. Try rendering in a different way. See what kind of quality you can get. Can you make large scale prints out of it, go and look at the processing version. There's a variety of things that you can look at and try to expand upon this. Maybe you can make a bunch of sliders to change different parameters and that sort of thing. So I hope you enjoyed this particular coding challenge. It was a little bit long, a little bit scattered. If you liked it, like the video, say it in the comments. Let me know on Twitter @Schiffman, and I look forward to seeing you in another coding challenge soon enough. Thanks for watching. Bye. Okay, everyone. I see there's like an elaborate chat going on. Whoops, about, I knocked over a fan. I see there's something elaborate going on in the chat. Yeah, I should do the, not a part of that video, but yeah, let's add the, let's get back to something reasonable that will run fast enough. And let's very quickly let's add some rainbow colors, just because we can. Sketch, color mode. Let's play the rainbow music, maybe. I'm too tired. My voice is gone. I have a cold. I feel like the alpha is too light. Gotta get this happening faster. Okay, there we go. This is the rainbow Perlin Noise flow field. This will be a good thumbnail. Okay, so I am going to leave. Oh my God, it's 1:45. This has been 2.5 hours. I'm going to get going. And I said I was going to go over Nature of Code and Magic Book. I'm going to just talk about that in the Slack channel. So I'm just going to plug for a second my Patreon. If you're interested in supporting the work that I do with this Coding Rainbow channel, you can go to codingrainbow.com. Right here, there is a link, become a patron. You can subscribe on Patreon. I'm getting a little bit of extra income for the channel, which actually the first thing I want to do is just use that money to pay for closed captioning, but I haven't reached a sort of high enough threshold to have enough to do that. And then I have a Slack with a subscription here. I have a Slack channel where we discuss topics and various things, we've had a discussion about the JavaScript version of the Nature of Code book, which I meant to also discuss on the live stream today, but I'm not going to really have time to do that right now. So here is Perlin Noise flow field rainbow. I definitely need a GIF with this. So I think what might help would be to have some music. Where am I in front of the rainbow here? Right? Wait, how's it go? It goes like this. This is like the swimming thing. Thumbnail. Okay. I think that's maybe it for today. So unfortunately, I've got to run. If I maybe can take like 1 or 2 questions in the chat. I apologize for today being all about Perlin Noise if that didn't interest you. I apologize for today being a bit scattered. Just cold has made my head a little bit cloudy. The heat. This week is a little bit busy, unfortunately. So I think this is probably my only live stream for this week. Although there's a small chance that I'm going to be able to do something brief tomorrow. Because one of the things that I'm doing tomorrow in this space is actually recording programming tutorials for hearing impaired with somebody who does sign language, which is a project that is being spearheaded by Taeyun Choi called Signing Coders. But I'm just going to show you guys this. I'm going to look Signing Coders. I encourage you to check out Taeyun's work with assistive technology and programming tutorials if you go to this URL. He has a lot of materials and different stuff, and we're going to record some video tutorials tomorrow. We're not going to live broadcast that because I'm not really sure how it's going to work yet. So that's going to happen tomorrow. So I might have some time around doing that to do a quick live stream. But typically I've been doing these Tuesday and Friday. This Friday is my son's 8th birthday, so I have commitments at his school to help with a bunch of things. So I won't be able to be down here at my video recording studio. So thanks. There is I'll show you just briefly what's coming next. I haven't released the super shape tutorial, the two-dimensional super shape tutorial. I've been working on 3D super shapes. I had help from Oliver in the chat. And so if I have a quick moment tomorrow, I might do that tutorial. And July 4th coding challenge. Yeah, we should do fireworks for July 4th. I mean, it's a little cheesy, but that's I got to remember to do that. So I should do a July 4th. I'm going to be out of town for July 4th, the actual date. So next week, somebody remind me, I'll try to do July 4th fireworks. Okay, any last, Rebubble asks, why is this live video always the same? Because I don't know. I'm an old dog with the same tricks. I don't know what the expression is. I've got time for a few more questions here on
Cutting Rainbow.
Coding Rainbow.
with me.
The Schiffman.
Okay. Oh, a coding challenge in French for July 14th, Bastille Day. I will be back in town. Okay, I really like the idea of doing this. There's a lot of French listeners, and I do sort of speak French. The problem is the last time I really, when I was in 9th grade, which would be many years ago, and at the age of 14 or something, I lived in the French part of Switzerland for a summer in a little town called Éponge, which is near Yverdon-les-Bains in the French part of Switzerland. And I was quite good at French at that time because that's all I spoke, but it's mostly all gone. So could I actually do programming in French? Let's just try it for a second. Bonjour. Aujourd'hui, je fais le programme, le code. Voilà le Atom, le éditeur Atom. C'est un particle. Oui. Peut-être je change qu'est-ce que ligne? La ligne? I don't know. Nope. Rectangle? I'm just taking English words and pronouncing them with a French accent. Okay, so you can see how disastrous this might be. I'll have to study up. I need to get you guys to give me a cheat sheet of common. I think this kind of French that I know isn't really the technical stuff. I'm kind of lost. I could do the counting though. This dot H. How do you say H in French? A, B, C, D, E, F, W is W. Anyway, ligne, I got it. Okay. Anyway, that's as far as I can do it right now. Okay, any other last questions? Okay, I'm gonna go. I don't know what will become of today's live stream. But math blanks are Mathieu, who does an amazing job of somehow turning these various things into the mess of the live stream into like separate videos. Will do his magic, and I'll be communicating with you on Twitter and over the Slack channel when I'm releasing new video tutorials. Okay, and I will see you guys soon. Thank you for watching. Thank you for being patient and accommodating. Thank you for keeping it friendly in the chat. Seemed to work pretty well today. And we had some little glitches at the beginning, but that's that. Okay. Yes. 10, 11, 12. Oh, AM and PM. I don't remember. Yeah. Okay. So I'll see you guys later. The next live stream will most likely be next Monday or Tuesday. Actually, next Tuesday mostly, a week from today. Though it's possible I'll sneak one in another point this week if I can. But hopefully I'm going to have time to sort of get all the code out there, to work on the JavaScript version of Nature of Code and other stuff like that. Okay? I'll see you guys. Thanks for watching. Appreciate it. I'm back briefly because I forgot there was a request for 11, 10, 11, 12, and AM and PM, right? Okay. 10, 11, 12, AM. No, I don't like that one. AM, PM. 10, 11, 12, AM, PM. 10, 11, 12, AM, PM. Use whatever you want. Okay, goodbye.